In this problem, you see a block of mass M is held at rest on an inclined plane making an angle theta above the horizontal. There exists friction between block M and the plane. Block M is connected to a second block of mass m by a massless cord that passes over a frictionless massless plane. In part A, we will draw the free body diagram of each block. In part B, we will find the magnitude of the acceleration of the blocks using the numerical values. Capital M equals 320 grams, small m equals 280 grams, angle theta equals 34 degrees, coefficient of static friction μs equals 0.31, and coefficient of kinetic friction μk equals 0.19. Finally, in part C, we will find the speed of block M when it falls 22 cm. In part A, we draw free body diagrams. For mass M, we represent it by a point. Then the inclined plane and inclination angle theta are drawn. The gravitational force is a downward force and its magnitude is M times acceleration vector g. Tension force T is drawn in the direction pointing the cord. It is now parallel to the surface as observed. The normal force, denoted by N, is drawn perpendicular to the surface. Finally, assume that there is a motion in the direction parallel to vector t with an acceleration vector, say a. Then we can claim that there is no static frictional force. Instead, there is a kinetic frictional force called vector fk in the opposite direction to the motion. For convenience, let's decompose gravitational force along the lines perpendicular to the inclined surface and parallel to the surface. Angle theta is carried here. The component perpendicular to the surface becomes M times g times cosine theta, and the other parallel to the surface becomes M times g times sine theta. Now we are to draw the free body diagram of mass m. The gravitational force on the object is a downward force as indicated here. Its magnitude is m times g. The tension force is in the direction pointing the cord, denoted by T prime, and its magnitude is the same as that of tension force T. Finally, since we choose the direction of the motion in this direction for mass M, then the motion of m is in the downward direction. We show its acceleration vector by vector A prime, keeping in mind that its magnitude is the same as that of vector A. Okay, these are the free body diagrams of each block. Let's solve part B. In part B, we are going to calculate the magnitude of the acceleration of the blocks. First of all, let's calculate the normal force on mass M. Only this force, lying on the same straight line with the normal force, is of our concern. Thus, according to the configuration, the magnitude of vector n is determined to be m times g times cosine theta. And let's label this equation as 1. The equation of motion for block capital M is found by the Newton's second law, which is F net equals m times A. We have only the motion along this line. Therefore, net force is F net equals T minus capital M times G times sine theta minus Fk, which is equal to capital M times A. And let's label this equation as 2. Next, we write the equation of motion for small m as follows. Vector F net is the total force in the direction of acceleration vector. It is found by the difference m times g minus t, which is equal to m times a with the help of Newton's second law. And let's label this equation as 3. And finally, the kinetic frictional force is calculated by the formula Fk equals mu k times n, or equally by equation 1 for n, we have Fk equals mu k times capital M times g times cosine theta. And let's call this equation as 4. In order to progress, let me use a new page. Here we have two equations of motion and two unknowns, which are tension T and acceleration A. To find an expression for A, we eliminate T by adding equations 2 and 3 side by side. As a result, we get small m times g minus capital M times g times sine theta minus Fk, which is equal to capital M plus small m times A. Put the value of Fk in equation 4 into here to obtain small m times g minus capital M times g times sine theta minus mu k times capital M times g times cosine theta, which is equal to capital M plus small m times A. Now divide both sides by capital M plus small m and finally get the desired formula for A as small m minus capital M times sine theta plus mu k times cosine theta times g over capital M plus small m. After performing appropriate unit conversions, substitute the corresponding numerical values into this equation such that A equals 0.28 kilograms minus 0.32 kilograms times sine of angle 34 degrees plus 0.19 times cosine of angle 34 degrees times 9.80 meter per second squared divided by 0.32 plus 0.28 kilograms, which results in A equals 0.82733 meter per second square, which is approximated as 0.827 meter per second squared. Note that in the intermediate step, we wrote the result in 5 digits, where we don't count the first zero, and the final result is in 3 digits, and again we don't count the first zero. Okay, this is the answer to the question in part B, and let's see part C. Notice that each block moves in one dimension. We are asked to find the speed of block small m when it falls h equals 22 centimeters, which has to be converted into meters as 0.22 meters. We use the formula found in chapter 2, which relates velocities to acceleration and distance only. That is, v square equals v0 square plus 2a times delta x. Here we adjust this equation to our problem as v square equals v0 square plus 2 times a times h, or since the blocks are initially at rest, then we obtain v square equals 2 times a times h. Therefore, the formula for speed will be v equals square root of 2 times a times h. Finally, we put the corresponding values here as square root of 2 times 0.82733 meter per second squared times 0.22 meters, which is approximately 0.603 meter per second. Alright, this is the end of the discussions about problem 5, and let's solve the last problem.